What if Saturn's rings, the most beautiful crown in our solar system, are not permanent at all? Welcome to Sleepy Space. Tonight, we'll drift quietly into the mystery of why Saturn's rings are disappearing, what Cassini discovered, and why we may be living at the perfect time to see them. Before we begin, tell us where you're watching from, and gently subscribe and like if you enjoy peaceful space stories. Imagine looking at Saturn through a quiet telescope late at night, when the house is still, the room is dark, and the planet appears not as a place you could ever touch, but as a pale, golden thought suspended in blackness, carrying around itself the most famous ring system in the solar system, so wide that it could span much of the distance between Earth and the Moon if placed near us, and yet so thin, so delicate, so strangely fragile that from the wrong angle it can almost vanish into a line of light. This is the first truth behind the phrase that Saturn's rings are disappearing. And it is the gentler truth, because every 15 years or so, as Saturn continues its slow 29-year journey around the Sun, and Earth shifts its own smaller orbit inside that larger rhythm, we begin to see the rings edge on, not as a broad tilted disk, but as an almost razor-thin sheet. And the great shining halo that once made Saturn look like a crowned world seems to fade away, not because the rings have suddenly dissolved, but because geometry has turned their vastness sideways, reminding us that even the most magnificent object in the sky can become nearly invisible when the angle of seeing changes by just a few degrees. Yet, that optical disappearance is only the doorway into the deeper and more unsettling story. Because Saturn's rings are not merely hiding from our line of sight, they are also being physically eroded, grain by grain, molecule by molecule, through processes so slow that no human life could watch them happen, but so persistent that on the time scale of planets, they become a kind of cosmic weathering. And the central answer is this: Saturn's rings are disappearing because they are not a permanent solid structure, not a frozen crown locked in place forever, but a moving disk of countless icy particles caught between gravity, orbital motion, sunlight, magnetic fields, tiny impacts, and the long patience of celestial mechanics. Each ring particle, whether smaller than dust or as large as a boulder, is not resting above Saturn like decoration, but orbiting according to the same basic rule that governs moons, spacecraft, and planets, where the inward pull of gravity is continuously balanced by sideways motion, so that the particle keeps falling around Saturn rather than falling straight into it. And in the simplest mathematical sense, its orbital speed is tied to distance by the square root of Saturn's gravitational parameter divided by radius. A quiet little relationship that means closer particles travel faster, farther particles drift more slowly, and the ring system becomes not a rigid wheel, but a flattened river of ice, with inner lanes moving ahead of outer lanes in a silent shear that is continued for ages. This alone makes the rings vulnerable, because a river made of particles can collide, spread, clump, thin, darken, and leak. And unlike a moon, which has enough self-gravity to hold itself together as one body, the rings exist inside a region where Saturn's tidal forces can prevent loose material from easily gathering into a stable moon. So their beauty depends on a balance that is elegant but never final. From Earth, that balance looks calm, almost eternal. But up close, it would be restless in miniature, filled with faint impacts, charged grains, spiral density waves, gaps carved by resonances, and particles constantly negotiating their place in a disk where gravity writes the music and collisions keep time. The reason this becomes worse than most people imagine is that the rings are not simply changing shape. They are losing mass to Saturn itself through a process often described as ring rain, an almost dreamlike phrase for a very real physical pathway in which small icy particles in the rings become electrically charged by ultraviolet sunlight from the sun, or by interactions with plasma and micrometeoroid debris. And once charged, they no longer respond only to gravity and orbital motion, but also to Saturn's magnetic field, whose invisible lines curve down toward the planet like dark strings pulled through space. When the balance of forces on these tiny grains shifts, some of them are guided out of the ring plane and downward along magnetic field lines, falling into the upper atmosphere where the ice vaporizes. Water-related molecules enter the ionosphere, and the rings quietly feed the planet that has held them for so long. There is something almost haunting about that image, because the same planet that makes the rings possible is also helping to draw them inward, and the same magnetic environment that gives Saturn one of its grand planetary identities also opens a route by which the ring material can be removed. The first strong hints of this did not arrive as a single obvious photograph of rings falling like rain, because space rarely gives its secrets in such simple pictures, but through patterns that needed interpretation, including Voyager-era observations of unusual dark bands and ionospheric behavior, later connected to the idea that water products from the rings were entering Saturn's atmosphere at specific magnetic latitudes. And decades after Voyager, more sensitive observations in infrared light revealed emissions associated with H3+ ions, a signal that allowed scientists to infer where charged ring-derived material was interacting with Saturn's upper atmosphere. Then Cassini, during its final months, moved through the region between the planet and the rings, a place no spacecraft had sampled so intimately before, and its measurements deepened the story by showing that material from the rings was not a poetic metaphor, but a measurable exchange between disk and planet. This is why the disappearance is not just visual, not just seasonal, not just a trick of viewing geometry, because there is an actual mass budget hidden behind the glow. And when scientists estimate how much material is draining away, the numbers suggest that the rings may survive for only a few 100 million years, perhaps less under some combined loss scenarios, which sounds enormous until it is compared with Saturn's age of more than 4 billion years. And suddenly, the rings no longer feel like an ancient, guaranteed feature of the planet, but like a temporary phase in a much longer life. That possibility becomes even more striking when we consider their brightness. because Saturn's main rings are made largely of water ice, and clean water ice reflects sunlight beautifully, which is why the rings appear so luminous compared with the darker, thinner ring systems of Jupiter, Uranus, and Neptune. Yet, the solar system is filled with micrometeoroid dust, tiny dark contaminants drifting through interplanetary space. And over vast time, those particles should steadily pollute the rings, making them darker and more chemically mixed, the way fresh snow becomes gray when exposed to dirt and exhaust. If Saturn's rings had been exposed in their present form since the birth of the solar system, many models suggest they might look older, heavier with pollution, less startlingly bright. So their purity becomes a clue, and perhaps a warning, that they may be far younger than Saturn itself. Maybe the aftermath of a disrupted icy moon, a collision, or some other dynamical event that placed a great amount of frozen debris inside Saturn's tidal domain. This is not settled in every detail, and careful scientists still treat the age problem as a system of linked uncertainties involving ring mass, dust influx, recycling, viscous spreading, ballistic transport, and the rate at which material falls into the planet. But the broad picture is powerful enough. The rings appear to be evolving, losing, and possibly young, not a fixed emblem from the beginning of time. So when we ask why Saturn's rings are disappearing, we are really asking a layered question about visibility, motion, erosion, and time, beginning with the simple fact that an extremely thin disk can nearly vanish when seen edge-on, moving into the deeper fact that charged grains can rain into Saturn along magnetic pathways, and arriving finally at the most humbling possibility that the universe allowed us to see Saturn during one rare interval when its rings are spectacular, bright, and still present. If an intelligent observer had looked at Saturn too early, perhaps the rings might not yet have existed in this form. And if another observer looks too late, perhaps the great white arcs will have thinned into faint remnants, leaving Saturn still immense, still beautiful, but missing the feature that made generations of humans stop and stare. That is the quiet force of this story. Not panic, not catastrophe, but impermanence on a planetary scale. Because the rings are vanishing slowly enough to feel eternal, and quickly enough, by cosmic standards, to be temporary. And somewhere inside that contradiction is the reason Saturn feels more mysterious the more we understand it. A world whose crown is made of ice, whose ice is made of fragments, whose fragments obey mathematics, whose mathematics becomes rain, and whose rain falls so softly into the atmosphere of a giant planet that only patient instruments, long missions, and human curiosity could ever notice that the most beautiful ring system we know has been leaving all along. If you could drift silently toward Saturn, past the faint amber haze of the outer solar system, and lower yourself toward the immense shining plain that surrounds the planet, the first surprise would be that the rings would not look like a solid road of ice, or a polished celestial bracelet, or a smooth white disk waiting to be crossed. Because the rings of Saturn are not really a thing in the ordinary sense of a thing. They are a system, a crowd, a river, a nearly flat swarm of countless separate particles, each one moving on its own orbit around Saturn, each one obeying gravity with quiet precision. And together, they create from a distance the illusion of one continuous band of light. This is the deeper answer to what Saturn's rings truly are, and it matters because anything made of separate orbiting fragments can evolve, leak, collide, darken, spread, and eventually disappear in ways a single solid object could not. The rings are mostly made of water ice, mixed with smaller amounts of rocky material, dust, and darker contaminants. And that icy composition is why they shine so beautifully under sunlight, reflecting a pale brightness that makes Saturn look almost ceremonial, as if the planet were wearing a crown. But when science looks closer, the crown dissolves into pieces, and the pieces become data. Grains as small as smoke-like dust, pebbles, icy clumps, boulder-sized bodies, and in some regions, possibly larger aggregates or embedded moonlets that disturb the surrounding material like stones beneath a shallow stream. The poetic mistake is to imagine the rings as still, because every particle in them is traveling at orbital speed, and the closer it is to Saturn, the faster it must move, following the simple Keplerian rule that orbital velocity decreases with distance. So the inner ring particles race ahead while the outer ones lag behind, producing a constant shear across the disk, a slow celestial sliding in which neighboring lanes of ice are never quite moving together. This differential motion is one of the basic mechanical truths of the rings, and it turns the system into a living laboratory of orbital dynamics. Because the rings are flat, not because someone placed them that way, but because collisions and angular momentum have gradually organized the material into Saturn's equatorial plane. Just as a spinning cloud of debris tends to settle into a disk when random vertical motions are damped away by repeated impacts. Each collision is usually gentle compared with the violence of planetary formation, but over thousands, millions, and possibly hundreds of millions of years, those countless small touches act like a kind of cold friction, draining disorder from the swarm and keeping the disk thin, bright, and spread out. And yet, even the word thin almost fails here, because the main ring system stretches across an enormous radial distance, while its vertical thickness can be astonishingly small by comparison. So if the rings were scaled down to the size of a sheet of paper spread across a room, the thickness would be less like cardboard and more like a whisper, which is why their beauty depends so strongly on viewing angle, and why they can nearly vanish when seen edge-on from Earth. Saturn's ring system is usually described by named regions, not because nature drew labels on it, but because telescopes and spacecraft revealed distinct zones of brightness, density, particle size, and dynamical behavior. Beginning close to the planet with faint inner material such as the D ring, then the more substantial C ring, the brilliant and massive B ring, the Cassini Division that is not truly empty but dramatically less dense, the A ring beyond it, and farther outward the narrow F ring, the faint G ring, and the enormous diffuse E ring associated with Enceladus. Each region has its own character, and the differences are not decorative, because brightness can indicate particle concentration, optical depth, composition, and the way light scatters through the disk, while gaps and edges often reveal the hidden influence of moons, resonances, and gravitational timing. The famous Cassini Division, for example, looks like a dark break between the A and B rings, but it is better understood as a region where orbital resonances, especially with the moon Mimas, help remove or redistribute material, showing that the rings are not merely sitting near Saturn, but being carved by mathematics, with repeated gravitational tugs occurring at precise orbital ratios, like a soft rhythm played over immense time. Nearby moons, such as Pan and Daphnis, actually live inside ring gaps, opening lanes and raising waves along ring edges, while Prometheus and Pandora help shape the narrow F-ring, pulling streamers and braids of material into forms that look delicate in photographs, but are really expressions of Newtonian mechanics written in ice. In this sense, Saturn's rings are not a frozen picture, but a gravitational manuscript, and every gap, ripple, scalloped edge, spiral density wave, bending wave, and temporary clump is a sentence in that manuscript, written by the interaction between particle motion and the moons that orbit nearby. The more advanced view becomes even stranger, because the rings can behave like both a fluid and a granular solid without being either one completely, since individual particles collide like grains of sand, yet the collective disk supports waves, wakes, pressure-like behavior, viscosity, and transport of angular momentum, allowing researchers to borrow mathematical ideas from fluid dynamics while never forgetting that the fluid is actually made of separate icy bodies. In denser regions, especially in the A ring, the particles can organize into temporary, elongated clumps called self-gravity wakes, where mutual attraction gathers material into trailing structures that form and break apart continuously, changing how light passes through the rings and making their measured brightness depend not only on how much material is there, but on the angle from which the spacecraft or telescope observes it. This is why studying the rings is not as simple as taking a photograph and measuring whiteness, because scientists have had to use stellar occultations, radio signals, infrared spectra, spacecraft imaging, gravitational measurements, and models of light scattering to infer the size, distribution, density, and mass of material hidden inside a disk that looks simple only from far away. When Cassini watched stars pass behind the rings, the starlight blinked and dimmed through different layers, allowing scientists to reconstruct optical depth like reading the rings by their shadows. And when radio waves passed through them, the way those signals were absorbed and scattered gave clues about particle sizes and concentrations. Spectroscopy then added another layer by revealing the strong signature of water ice, not as a guess from color alone, but through the way molecules absorb and reflect specific wavelengths, turning the rings into a cold chemical archive. Still, that archive is not perfectly clean, because micrometeoroids constantly strike the ring particles, adding darker material and blasting tiny debris into new trajectories. And those impacts matter for the question of disappearance, because a ring system made of fragments is always processing itself, always grinding, coating, eroding, and rearranging, even when the human eye sees only serenity. The origin of this material remains one of the great careful uncertainties, with several plausible pathways still debated, including the breakup of an icy moon that wandered too close to Saturn, the destruction of a comet or captured body, or a more ancient reservoir of debris that has been recycled over time. But all versions must answer the same physical constraints. The material has to be rich in ice, located inside or near regions where tidal forces prevent easy accretion into a large moon, bright enough to appear relatively clean and dynamically shaped by the existing moon system. The Roche limit is central here, because within a certain distance from a massive planet, tidal forces can overcome the self-gravity holding a loose body together, meaning a moon or icy object that passes too close may be pulled apart, while loose debris already inside that zone may struggle to assemble into a stable moon. And this gives the rings their strange halfway identity. Not quite a moon, not merely dust, but matter suspended in a region where gravity both organizes and forbids completion. Even the large E-ring tells a different but related story, because it is fed by icy particles escaping from the geysers of Enceladus, demonstrating that Saturn's ring environment is not one single object with one single origin, but a family of structures with different sources, lifetimes, densities, and particle populations. The main rings are dense, bright, and sharply structured, while the diffuse outer rings can be ghostly and broad, shaped more strongly by radiation pressure, plasma, and moon-supplied dust. So the phrase, Saturn's rings, hides an entire architecture of physical regimes. And once we understand this architecture, the idea that the rings are disappearing becomes more profound, because we are no longer imagining a solid halo breaking apart, but a complex orbital ecosystem slowly losing material through collisions, electromagnetic forces, micrometeoroid pollution, viscous spreading, and ring rain into the planet, with every process acting on a different size of particle and a different timescale. In the quietest possible way, the rings are both structure and process, both object and event, both a visible wonder and a temporary arrangement of matter that has not settled into a moon and has not yet fallen into Saturn. This is why their beauty feels almost impossible after you understand them, because what looks like a perfect white ring is actually billions upon billions of small frozen histories moving at kilometers per second around a hydrogen-helium giant held in place by orbital mechanics, sculpted by moons, brightened by ice, darkened by dust, measured by spacecraft, and slowly transformed by forces too patient to notice in a single lifetime. So the true identity of Saturn's rings is not a crown, but a question still unfolding. A luminous debris field caught in a delicate compromise between formation and loss. And when we look at them from Earth, we are not seeing something permanent attached to Saturn, but a temporary page in the planet's long biography, still glowing tonight, still circling in silence, still teaching us that the most graceful structures in the universe may be the ones that are never completely still. The reason Saturn's rings can become so thin to our eyes that they almost vanish is not because they are small, and not because they are weak in any simple sense, but because they are one of the most extreme examples in the solar system of a structure that is enormous in width and almost impossibly slight in height. A luminous disk so broad that it stretches hundreds of thousands of kilometers across space, yet in the main rings is often only about the height of a small building from top to bottom. And when something that wide is also that thin, the universe gives it a strange kind of invisibility, because from above, it can look like a shining, frozen plane, while from the side, it can collapse into a line finer than a scratch of light across the planet's face. If you imagine holding a sheet of paper in a dark room and turning it slowly under a lamp, the face of the paper first catches light as a bright surface, then narrows, then becomes almost nothing when its edge points directly toward you. And Saturn's rings behave in a similar geometric way, except the paper is made of billions upon billions of ice particles. The lamp is the sun. The room is the outer solar system. And the observer is Earth, drifting through its own orbit, while Saturn moves slowly through a year that lasts nearly 3 decades. This edge-on illusion is called a ring plane crossing, and it occurs because Saturn's equator and ring plane are tilted relative to the path Saturn follows around the Sun. So as Saturn orbits, we do not always see the rings at the same angle, but watch them open and close like a quiet celestial fan, wide and brilliant at one season, narrow and subdued at another, until for a brief period, Earth lies close to the same plane as the rings, and the great halo seems to disappear. The key is that the rings do not need to move very much to change dramatically in appearance, because their vertical thickness is tiny compared with their radial extent. And in geometry, apparent area depends on projection, meaning the visible surface of a tilted disk is roughly related to the sine of the viewing angle. So when the angle becomes small, the area reflecting sunlight toward us shrinks rapidly, and the ring system that once spread outward on both sides of Saturn like a glowing bridge becomes a hairline, a thin mark hidden in the glare of the planet and the darkness around it. Yet, this visual disappearance has a physical origin deeper than mere perspective, because the rings are thin in the first place, for reasons rooted in angular momentum, collisions, and the self-organizing behavior of orbiting debris. When a cloud of particles moves around a central body like Saturn, every particle can begin with a slightly different inclination, a slightly different vertical motion, a slightly different path above or below the equatorial plane. But over time, as those particles collide, their random vertical motions are damped, because impacts convert some organized motion into heat, fracture, spin, and small-scale disorder, while the total angular momentum of the disk remains oriented in a dominant direction. The result is that the swarm settles, not instantly, but statistically, into a flatter and flatter arrangement, a disk where most particles orbit close to the same plane, just as a shaken cloud of dust around a forming star can settle into a protoplanetary disk, or debris around a planet can flatten into rings. The process is not mystical, but it is beautiful in the way simple mechanics can become architecture, because every soft collision between icy fragments acts like a tiny correction, reducing the height of the swarm and helping the system remember one preferred plane. Saturn's equatorial bulge strengthens this tendency, since the planet is not a perfect sphere, but an oblate rotating giant, wider at the equator than from pole to pole. And that uneven gravity field causes tilted orbits close to the planet to precess, meaning their orbital planes slowly rotate around Saturn's spin axis. So, over long times, the stable reference plane for the dense main rings becomes closely tied to Saturn's equator, rather than to some random orientation in space. This is one reason the rings feel so cleanly aligned, so mathematically disciplined, as if a giant invisible hand had pressed them flat, though the hand is really the combined influence of rotation, gravity, collisions, and time. A ring particle lifted too far above the main plane does not remain part of some permanent high cloud unless specific forces maintain it there, because it crosses the dense ring layer again and again, and each crossing increases the chance of collisions that drain away vertical energy. So the disk becomes vertically cold, not cold only in temperature, but cold in the dynamical sense, with low random speeds, compared with the enormous orbital speed around the planet. That distinction matters because the particles are racing around Saturn at many kilometers per second. Yet, relative to neighboring particles in similar orbits, their motions can be gentle, controlled, and narrow, allowing the disk to remain thin without flying apart. The rings are therefore not thin because nothing is happening inside them, but because too much has happened for too long in a way that suppresses vertical disorder, leaving behind a flattened structure that still contains ripples, waves, clumps, and disturbances, but is overall one of the most delicate large-scale systems humans have ever studied. Cassini made this delicacy more real by showing that even during times when the rings appear almost perfectly flat, they are not mathematically smooth, because embedded moonlets and gravitational resonances raise vertical structures, cast long shadows near Saturn's equinox, and reveal features that rise above the ring plane, like tiny mountain ranges on an otherwise thin sheet of ice. Those shadows were especially important because when sunlight strikes the ring's edge-on, even small vertical relief becomes exaggerated, and structures only a few kilometers high can cast shadows across vast distances, allowing scientists to measure height in a system where direct thickness is otherwise difficult to perceive. This is one of the elegant reversals of ring plane geometry. The same alignment that makes the rings nearly vanish from Earth can make their hidden vertical structures easier for a spacecraft to detect, because low sunlight turns small elevations into long, dark signatures. The rings also contain strange radial and vertical patterns known as bending waves, density waves, corrugations, and spokes, each produced by different physical causes, from moon-driven resonances to electrostatic lifting of tiny grains. And these features remind us that thinness does not mean simplicity, because a violin string is thin and still carries music. A sheet of water is thin and still carries waves, and Saturn's rings are thin enough to disappear visually, while complex enough to preserve a record of forces passing through them. Historically, this thinness helped confuse the first observers, because Galileo in 1610 saw Saturn through a telescope too primitive to resolve the rings clearly, and described odd side structures that seemed to change or vanish. And only later did Christian Huygens understand that Saturn was surrounded by a detached ring, while Giovanni Cassini revealed that the ring system itself had divisions, showing that the object which appears from far away as one smooth shape was actually more layered and precise than early eyes could know. Those early disappearances were not failures of imagination, but honest encounters with geometry, because when the rings close toward edge-on, even a good telescope could make them seem reduced, altered, or gone. And the planet that once looked adorned could suddenly look almost naked. In modern terms, we can describe this using inclination, optical depth, and scattering, because the brightness of the rings depends not only on how much material is present, but on how sunlight enters the disk, how particles reflect or transmit that light, how much ring area is projected toward the observer, and whether the near-edge perspective forces our line of sight through a denser path of particles even as the visible face shrinks. This makes the disappearance subtle, not a simple on-off switch, because the rings can become faint, thin, difficult, asymmetric, or temporarily masked by Saturn's own brightness and by the Sun's position in our sky. During some ring plane crossings, Earth may pass through the plane more than once because of the combined geometry of Earth's orbit and Saturn's slow motion. And these intervals have historically been valuable for finding small moons, since the glare from the bright rings drops away and faint objects near Saturn become easier to detect. So the disappearance is not merely a loss of spectacle, but a scientific opportunity. A moment when Saturn reveals different secrets precisely by hiding its most famous feature. And still, the deeper reason this chapter matters is that the visual vanishing prepares us to understand the physical vanishing. Because the same quality that lets the rings disappear from sight, their extraordinary thinness, their particle nature, their dependence on delicate orbital balance, also makes them vulnerable over long time, not because they are fragile like glass, but because they are fragile like a pattern, stable only while many small conditions continue to hold. A moon is a consolidated world, but a ring is an agreement among fragments, and agreements can be slowly rewritten by collisions, radiation, plasma, micrometeoroid impacts, resonances, and the planet's magnetic field. When we see the rings edge on, we are watching an optical preview of impermanence, a brief rehearsal of absence, where nothing catastrophic has happened, and yet the symbol of Saturn has nearly faded from view. It is a quiet lesson in scale, because a structure can be larger than worlds and still vanish by turning sideways, can be made of countless moving bodies and still look like one smooth line, can appear eternal in a textbook and yet depend on angles so precise that a few degrees can change majesty into almost nothing. This is why Saturn's ring plane crossings feel so strangely moving, because they do not show us the rings being destroyed, but they reveal how little thickness separates visibility from disappearance, how much of beauty depends on alignment, and how the grandest sights in the solar system are not simply objects floating in darkness, but relationships between light, matter, motion, and the position from which a small planet happens to be watching. The phrase ring rain sounds almost too gentle for what it means, as if Saturn were quietly receiving a silver drizzle from its own crown. But hidden inside that soft image is one of the most important reasons the rings are not eternal. Tiny pieces of the ring system are being removed from their orbits and guided down into Saturn's upper atmosphere. Not in a storm we could see with the naked eye, not as bright streaks falling through clouds, but as a silent chemical and electromagnetic flow, where grains of water ice charged molecules and dusty fragments leave the thin ring plane and follow the planet's invisible magnetic architecture inward. To understand why this happens, we have to begin with the fact that ring particles are not neutral actors floating peacefully forever in pure gravity. Because Saturn's environment is not empty space, but a magnetosphere, a vast domain shaped by the planet's rotating magnetic field, filled with plasma, charged particles, radiation, and material supplied by moons like Enceladus, while sunlight itself is constantly striking the icy grains and altering their electrical state. In the simplest picture, a ring particle orbits Saturn because gravity pulls inward, while its sideways velocity carries it forward. So the particle keeps falling around the planet in a stable path. But the moment that particle becomes electrically charged, another layer of physics enters the story. Because a charged particle moving through a magnetic field feels the Lorentz force, often written as Q times the velocity crossed with the magnetic field. And although that compact mathematical expression looks almost weightless on paper, around Saturn it can become a slow doorway through which microscopic ice is removed from a giant ring system. The charge may come from ultraviolet sunlight knocking electrons loose, from impacts with energetic plasma, from collisions that expose fresh icy surfaces, or from micrometeoroid bombardment that vaporizes and ionizes tiny bits of ring material. And once a grain or molecule is no longer purely neutral, its path is no longer governed only by the elegant curve of Keplerian orbit, but by a complicated negotiation among gravity, centrifugal motion, electric fields, magnetic field lines, collisions, and the drag of Saturn's upper atmosphere. This is why ring rain is so fascinating, because it is not one single mechanism acting like a drain at the bottom of a bathtub, but a family of linked processes that slowly convert orbiting ice into atmospheric chemistry. Some of the material begins as water ice in the rings, then becomes charged water group particles or molecular fragments. And as Saturn's magnetic field lines connect regions of the rings to specific latitudes on the planet, those particles can spiral or stream along those lines toward the ionosphere, the high atmospheric layer where sunlight and energetic particles create ions and electrons. When water from the rings arrives there, it changes the balance of Saturn's ionosphere, because water-related molecules can remove free electrons through chemical reactions, suppressing electron densities in ways that early models of Saturn's atmosphere did not fully explain. This was one of the clues that something from the rings was raining down, not visually as falling snow, but chemically, by altering the faint glow, temperature structure, and charged environment of the atmosphere below. Long before Cassini's final dive, the Voyager flybys in the early 1980s gave hints that Saturn's rings might be losing material at a significant rate, and later ground-based observations, including infrared studies of H3+ emissions in Saturn's ionosphere, helped map patterns that matched magnetic connections to the rings, showing that this was not a local oddity, but a broad planet-ring exchange. The pattern mattered because if the upper atmosphere were affected only by sunlight, scientists would expect a smoother distribution. But instead, they saw organized latitudinal features, like invisible rain bands, where the chemistry seemed linked to the structure of the rings above. In that sense, Saturn's atmosphere became a screen on which the rings wrote their disappearance, not with light that any casual observer could see, but with spectral fingerprints, emissions, and missing electrons. Cassini then brought the story closer, because during its grand finale, the spacecraft repeatedly passed through the narrow region between Saturn and the innermost rings, a dangerous and scientifically precious corridor that had never been sampled so directly. And its instruments detected material falling inward at rates that surprised researchers, including not only the charged ring rain inferred from earlier observations, but also a more complex flow of dust, nanograins, organics, silicates, and neutral material moving from the ring region toward the planet. This made the old image of ring rain richer and stranger, because the rings were not merely sending clean water downward like a pure icy mist, but a mixture of substances, a dusty chemical drizzle, carrying information about ring composition, surface contamination, micrometeoroid processing, and the long history of particles exposed to space. The numbers remain model-dependent, and scientists continue to refine how steady these flows are across seasons and solar activity. But even conservative interpretations point toward a real loss of ring material. And if such loss continues over astronomical time, the rings cannot remain unchanged indefinitely. The timescale often mentioned, roughly on the order of 100 to 300 million years for major disappearance under certain assumptions, sounds enormous, because it is far longer than all of recorded human history, longer than the age of mammals as dominant life on Earth, longer than the entire span separating us from many ancient ecosystems. Yet, against Saturn's lifetime of about 4.5 billion years, it is brief, almost like the final dimming of a candle during a very long night. This is the emotional and scientific weight of ring rain, because it changes the rings from a static symbol into an active exchange, a temporary reservoir of ice that is slowly being recycled into the planet. When a tiny charged grain leaves the ring plane, it does not know that it was part of one of the most beautiful structures in the solar system, and it does not fall with drama, but follows fields and forces, obeying the quiet geometry of magnetism, curving along paths that human eyes cannot see, until it reaches a region where orbital identity is lost and atmospheric identity begins. There may be no surface on Saturn for the particle to strike, no hard ground, no ocean, no mountain, only deeper and deeper layers of hydrogen and helium beneath swirling cloud bands. So the rain does not end in a puddle, but in chemistry, heat, ionization, and mixing. The same water ice that once scattered sunlight in the B ring or drifted near the Cassini Division may become a molecule in Saturn's upper atmosphere, part of an ion reaction, part of a spectral signature, part of a planet that is slowly consuming the evidence of its own adornment. The process also reveals why the rings are so difficult to treat as a simple object with a single lifetime, because large particles, small dust grains, nanograins, charged ions, and neutral molecules are each affected differently, and the removal of material depends on particle size, charge-to-mass ratio, location in the ring system, solar ultraviolet intensity, plasma conditions, micrometeoroid impact rates, and Saturn's seasonal geometry. A boulder-sized icy body may remain largely governed by gravity and collisions, while a micron-sized grain can become magnetically responsive, and a molecule released from an impact plume may move through chemistry rather than orbit. so the rings are disappearing through many channels at once, some broad and steady, some seasonal, some still uncertain. This is where the simple bedtime image of rain becomes an advanced planetary science problem, because what falls from the rings is not just matter, but angular momentum, electric charge, chemical potential, and information about how dusty disks evolve around massive bodies. The same principles that shape ring rain also echo in other astrophysical systems, from circumplanetary disks around young giant planets to debris disks around stars. Because whenever small particles orbit in a magnetic, radiative, collisional environment, they become vulnerable to forces that large bodies can ignore. Saturn gives us a nearby laboratory where those ideas can be measured, not merely imagined. And that is why this quiet loss matters far beyond one planet. Still, the most haunting part is the reversal hidden in the relationship between Saturn and its rings. Because the planet's gravity helped preserve the rings as a disk, its moons sculpted their edges and waves, its magnetic field organizes the space around them. And yet, those same fields and forces now help guide ring material downward, as if the system that displays the rings also contains the instructions for their removal. Nothing about this is sudden, and nothing about it needs to be exaggerated into disaster, but it is more unsettling precisely because it is calm, because the rings are not being smashed apart in a spectacle. They are being unmade by the normal operation of physics. Ring rain is the soundless evidence that beauty in space can be temporary without being fragile in the human sense, that a structure can endure for millions of years and still be in decline, that an object can look still because its motion is too fast and its loss too slow for our senses to hold together. So when we look at Saturn tonight, the rings may seem perfect, bright, and unchanged. Yet somewhere in that cold, flat disk, a grain receives charge, a path shifts, a magnetic line becomes a road, and a particle that once belonged to the shining crown begins its long descent into the planet below, adding one more invisible drop to a rain that has been falling in silence for ages, and may continue falling until the crown itself has thinned into memory. When Cassini entered the narrow darkness between Saturn and its innermost rings, it was not simply flying through empty space, and it was not simply ending a mission. It was passing into one of the most delicate measurement zones ever reached by a human-made spacecraft. A corridor only a few thousand kilometers wide compared with the vast scale of Saturn, bordered on one side by the pale edge of the D-ring and on the other by the high atmosphere of a giant planet with no solid surface. And in that dim region, where sunlight was scattered by ice, shadowed by rings, and softened by distance, Cassini began to listen in the only way a machine can listen. Not with ears, but with antennas, sensors, voltage changes, mass spectra, Doppler shifts, particle counters, and plasma waves translated into patterns that scientists could hear as sound. The phrase, "What did Cassini hear?" is partly poetic, but it is also surprisingly literal, because the spacecraft's radio and plasma wave science instrument could detect tiny dust particles striking its long antennas. And when those impacts were converted into audio, the data became little pops and cracks, like static, like sleet against metal, like the faint tapping of a storm too small for human skin to feel. Before the grand finale dives, Cassini had crossed ring regions where dust impacts came rapidly, hundreds of tiny hits each second in some encounters, and scientists expected that the region between Saturn and the rings might also be noisy with dangerous grains. So the spacecraft was turned to place its high-gain antenna forward like a shield, a golden dish becoming a protective face as Cassini dove into the unknown. But on the first pass through the gap in April 2017, the sound was not the expected crackle of heavy ring debris. And this was the first great surprise. The space between Saturn and its inner rings was far emptier of dust-sized particles than many had feared. So empty that the usual whistles and squeaks of plasma waves came through clearly, with only a few pings where a storm of impacts might have been. This silence was not a lack of discovery. It was the discovery itself. Because in planetary science, an absence can be as meaningful as a signal. And the near quiet of that passage told researchers that the inner gap was not a thick, hidden fog of ring particles, but a more structured environment. One where the material falling from the rings was filtered, sorted, charged, guided, or confined in ways that simple intuition had not captured. The gap was dark, but it was not empty of physics. Because Cassini was moving through a region shaped by Saturn's gravity, its magnetic field, its ionosphere, the edge of the ring system, and the faint downward traffic of material leaving the rings. Each instrument heard a different kind of silence, and each silence had a different meaning. Because the dust detector and plasma wave instrument were not only asking whether particles existed, but what sizes they were, how often they arrived, how they were electrically charged, and whether their paths were governed more by gravity, radiation pressure, electromagnetic forces, or collisions in the ring plane. The simplest model would have imagined ring particles as icy bodies orbiting peacefully until they either stayed in place or slowly spiraled inward. But Cassini's final measurements pushed the picture toward a more complicated system, where the rings and planet are connected by currents, nanograins, neutral molecules, charged particles, and chemical exchange. So the dark gap became less like a clean space between two objects and more like a borderland where one form of matter was being transformed into another. In that borderland, the ion and neutral mass spectrometer gave Cassini a different kind of hearing, almost a sense of smell, sampling the composition of Saturn's upper atmosphere and the material arriving from above. And what it found made the story of ring rain more chemically rich than a pure fall of water ice. There were signatures consistent with water and other volatile material, but also methane, ammonia, carbon-bearing compounds, and complex organics in the broader analysis of ring-derived influx, suggesting that what descends from the rings is not a clean, white snowfall, but a processed mixture, ice touched by dust, radiation, micrometeoroid impacts, and long exposure to the outer solar system. This matters because composition is history, and every molecule carries a clue about the environment that shaped it. So Cassini's final passes were not only measuring disappearance, but reading the memory of the disappearing material. Meanwhile, the spacecraft's trajectory itself became an instrument, because tiny changes in Cassini's motion, tracked by radio signals sent back to Earth, allowed scientists to refine Saturn's gravity field and separate the gravitational influence of the planet from that of the rings, a delicate measurement that helped estimate the mass of the ring system and therefore fed directly into the question of age. If the rings are less massive than once thought, and if they are being darkened by incoming dust and drained by ring rain, then their bright appearance becomes harder to reconcile with an origin billions of years old, though the full age problem remains linked to uncertainties in mass, pollution rate, recycling, and loss processes. Cassini therefore did something no telescope alone could do. It made the rings less like an image and more like a measurable system with weight, composition, current, dust, and exchange. The spacecraft also listened to Saturn's magnetic environment, and here the story grows stranger, because Saturn's internal magnetic field turned out to be astonishingly well aligned with its rotation axis, far more axisymmetric than planetary dynamo theory had comfortably expected, creating a deep puzzle about how Saturn generates and maintains its magnetic field. This alignment was not just a curiosity, because the magnetic field is part of the machinery that can guide charged ring material into the atmosphere, and any precise understanding of ring rain must pass through the shape and behavior of that field. Cassini's grand finale showed that Saturn and its rings are more interconnected than they appear from Earth, with evidence for electric currents linking the rings to the top of the atmosphere. So the planet and its crown are not separate ornaments in the dark, but a coupled electrodynamic system. This is one of the quiet revolutions of the mission, because the old view of rings as scenery gave way to a view of rings as active participants in the planet's environment, feeding the ionosphere, influencing chemistry, interacting with plasma, and possibly changing with time in ways that can be measured only by flying close enough to risk the spacecraft itself. The final orbits were designed with that risk in mind, because Cassini had already spent years transforming our knowledge of Saturn, Titan, Enceladus, the rings, the magnetosphere, and the icy moons. But its fuel was running low, and to protect potentially habitable moons from accidental contamination, the mission would end by sending the spacecraft into Saturn's atmosphere, where it would become part of the planet it had studied. Before that ending, the grand finale gave Cassini a set of orbits so scientifically valuable that they were almost like a second mission hidden inside the first, each dive threading the needle between ring and cloud, gathering data from a place that had been imagined, modeled, feared, and debated, but never directly sampled. What Cassini heard there was not one answer, but a sequence of revelations. First, the gap was quieter than expected in dust impacts. A big empty, where plasma sounds emerged through the lack of crackling debris. Second, the emptiness was not absolute, because smaller particles and ring-derived material were still present, moving inward in ways that revealed the fine sorting of the system. Third, the atmosphere below was receiving material from the rings, including chemically complex ingredients that forced scientists to reconsider how ring rain enters, ablates, vaporizes, or remains in tiny dust form. Fourth, the planet's magnetic and electrical environment was intimately tied to the fate of the rings, connecting beauty to circuitry in a way no painting of Saturn can show. And fifth, the rings themselves, once weighed and chemically sampled by inference and direct passage, looked less like a permanent crown and more like a temporary reservoir slowly being exchanged with the planet. The haunting part is that Cassini did not hear destruction in the dramatic sense, because there was no roar, no avalanche, no visible collapse of the rings, only sparse pings, plasma tones, chemical traces, and tiny deviations in radio tracking, the quiet language of systems changing on timescales too long for human perception. In this way, the dark gap between Saturn and its rings became almost philosophical without ever leaving physics, because it showed that a place can look empty and still contain a process, that silence can measure absence, that absence can become evidence, and that the disappearance of Saturn's rings is not written only in what falls, but also in what is missing where scientists expected dust to be. Cassini's final gift was to make Saturn more intimate and more mysterious at the same time, because the closer we came, the less the rings resembled a perfect icon, and the more they became a living boundary of ice, plasma, magnetism, and atmosphere. And when the spacecraft finally entered Saturn on September 15th, 2017, losing contact as it burned into the upper layers of the planet, the story did not close so much as deepen, because Cassini had carried back the sound of a near-empty gap, the chemistry of falling ring material, the gravity of a young-looking ring system, and the uneasy truth that the most famous rings in the solar system are not merely shining around Saturn, but speaking softly as they fade. The strangest thing about Saturn's rings may not be that they're disappearing, but that they may not have been there for most of Saturn's life. And once that possibility enters the mind, the familiar image of the planet changes in a quiet but permanent way. Because Saturn is ancient, nearly as old as the solar system itself, a giant world that formed more than 4 billion years ago from the same rotating disk of gas and dust that gave birth to the Sun, the planets, the moons, the asteroids, and the first cold architecture of our cosmic neighborhood, while the rings, so bright and famous that they feel inseparable from Saturn's identity, may be far younger, perhaps only a few 100 million years old, perhaps even younger in some interpretations, which would mean that for most of its existence, Saturn may have moved through the darkness without the magnificent halo we now consider its signature. This is not a claim to hold too tightly as a final answer, because the age of Saturn's rings remains one of the most carefully debated problems in planetary science. But it is a powerful question because it comes from evidence, not imagination, and the first clue is their brightness, that almost snowy brilliance that makes the main rings flash back sunlight with a purity that seems, at first glance, timeless. The rings are made mostly of water ice, and clean water ice is highly reflective, but space is not clean, and over millions and billions of years, the solar system sprinkles surfaces with micrometeoroid dust, dark silicate grains, carbon-rich material, and tiny impactors moving fast enough to scar, vaporize, coat, and chemically alter what they strike. So if Saturn's rings had been sitting in their present exposed form since the earliest era of the solar system, one might expect them to look far more polluted, darker, less icy, less innocent in their light. This comparison is often described with the image of fresh snow because new snow can glow beautifully under morning sunlight. But if it lies beside a road for long enough, dust and grit slowly gray its surface, and the rings seem, in many measurements, surprisingly clean for something that might be billions of years old. Cassini made this clue far more quantitative because the spacecraft did not merely photograph the rings, it measured their mass, studied their composition, watched their structure, sampled the dust environment near Saturn, and gave researchers the ingredients needed to turn a visual suspicion into a physical timescale. How much ring material exists? How much non-icy contamination is present? How quickly micrometeoroids arrive, and how efficiently that contamination is retained or removed. In the simplest form, the reasoning is almost intimate, like estimating how long a white cloth has been lying under a slow rain of soot, because if you know the rate of falling dirt, and you know how dirty the cloth is, then you can estimate an exposure age. But in the real ring system, every term in that sentence becomes difficult, since the incoming dust flux can vary, impact material can vaporize, ejecta can move outward or inward through ballistic transport. Some contaminants may be buried, diluted, recycled, or lost, and the rings themselves can spread and evolve while being polluted. Still, when Cassini's measurements of ring mass and micrometeoroid influx are combined with the low fraction of dark material in the rings, many studies point toward an exposure age of no more than a few 100 million years, which is young not in human terms, but in planetary terms. And this is where the story becomes almost unsettling, because a few 100 million years is long enough for mountains to rise and vanish on Earth, long enough for continents to drift and entire families of life to appear and fade. Yet, compared with Saturn's full lifetime, it is like a late note added near the end of a very long symphony. The gravity measurements from Cassini's grand finale sharpened the age question by helping scientists estimate the mass of the rings. Because the total mass matters deeply, a more massive ring system can absorb and dilute pollution longer, while a less massive ring system becomes contaminated more quickly under the same dust flux. And Cassini's results suggested that the rings are not massive enough to comfortably hide billions of years of darkening unless some cleaning, recycling, or selective loss process has been more efficient than standard assumptions allowed. This is why the phrase "younger than we thought" is not simply about one number, but about the balance between mass, color, composition, and time, with each measurement leaning on the others like stones in an arch. The same issue appears in the ring's ongoing loss, because if ring rain and other inward transport processes are draining material toward Saturn, then the present rings are not only clean-looking, but also ephemeral, and an object that is both bright and losing mass begins to look less like a relic from the birth of the solar system and more like the aftermath of a later event. Perhaps the destruction of an icy moon. Perhaps a collision between moons. Perhaps the tidal shredding of a body that crossed too close to Saturn. Or perhaps a more complex history in which older material has been recycled so effectively that its apparent youth disguises a deeper ancestry. None of these possibilities should be treated as settled beyond dispute, because ring science is full of systems where appearance, exposure, and origin can separate from one another, but each possibility carries a different emotional weight. If the rings are truly young, then Saturn's most iconic feature is not primordial but recent, a temporary bloom of debris in the late life of a planet. If the rings are ancient but continually refreshed, then their brightness is not youth but renewal, a long-running cycle in which moonlets form, break, grind, and return material to the disk. If the rings are old but kept clean because incoming micrometeoroids vaporize on impact and fail to remain embedded, then their whiteness may be less like fresh snow and more like a surface that refuses to hold dirt. A subtle physical trick that would let an ancient ring system masquerade as young. The debate is therefore not a weakness in the story, but part of its depth, because science becomes most beautiful when the evidence is strong enough to narrow the darkness, but not so complete that wonder is erased. Historically, Saturn's rings have always forced observers to revise what they thought they saw. From Galileo's puzzling side objects to Huygens' detached ring, from Cassini's division to Voyager's spokes, from Cassini's fine structure to modern dust and gravity constraints. And the age question belongs to that same tradition, where a familiar object becomes strange again under better instruments. There is also a hidden lesson in scale, because the rings look smooth from Earth, but their history is written in events too small and too numerous to see directly. A micrometeoroid strikes an icy grain at high speed. A plume of vapor and debris leaves the impact site. Darker material mixes into a surface layer. Ejecta follow slightly altered orbits. Angular momentum shifts grain by grain. And somewhere else in the disk, a particle becomes charged and begins the slow path towards Saturn's atmosphere. Over millions of years, those tiny transactions become a clock. But the clock is not perfect, because its gears are made of uncertain fluxes, evolving ring viscosity, particle size distributions, and chemical processes that may not behave the same in every ring region. The A ring, B ring, and C ring do not carry identical histories, and the dense B ring in particular complicates the picture because it may hide more mass, more structure, and more internal mixing than brightness alone can reveal, while the more transparent C ring may preserve other clues about bombardment and depletion. Even the ring's radial spreading matters, because particles collide and transfer angular momentum, allowing some material to drift inward and some outward. And this viscous evolution can change surface density over time, meaning the rings we see now may not have the same shape, mass, or optical depth they had when they first formed. The question, are the rings young, is therefore not simply asking for a birthday, but asking whether the present bright configuration is young, whether the material itself is young, whether the exposure to space is young, and whether Saturn has worn rings continuously or only in episodes. This layered uncertainty is exactly why the answer feels deeper than a headline, because a ring can have an apparent age, a dynamical age, a compositional age, and an origin age, and those ages may not all agree. Still, the strongest modern evidence has made one idea difficult to ignore. The rings are not a guaranteed ancient fixture in their current form, and they are not safely permanent in their future form, which places us in a rare observational window, perhaps looking at Saturn during a brief season when its rings are both spectacular and temporary. If they formed from a shattered moon, then what we call beauty may be the luminous aftermath of destruction. Ice fragments from a lost world spread into orbital order by gravity. If they are maintained by recycling, then beauty is not a single event, but a restless continuity, a system renewing itself while still leaking away. If they are older than they appear, then beauty is a deception caused not by falsehood, but by physics more subtle than our first models. In every case, the rings become more moving, not less, because their brightness is no longer just visual splendor, but evidence in an unsolved argument about time. And as Saturn turns slowly in the cold distance, carrying that pale disk around its equator, the question of age lingers like starlight on ice, asking whether we are seeing a newborn crown, a surviving ancient relic, or a temporary shape made by cycles we have only begun to understand. And perhaps that is why the possibility of young rings feels so profound, because it means the solar system is not finished making itself, not frozen after its violent beginning, not merely preserving old monuments, but still capable of sudden losses, late formations, quiet rearrangements, and immense beauty appearing long after the planets themselves were born. The origin of Saturn's rings is one of those questions that seems simple only from far away, because from Earth, the rings look so complete, so balanced, so naturally belonging to the planet, that the mind almost wants to believe they have always been there. A permanent crown placed around Saturn at the beginning of the solar system. But when the evidence is followed patiently, particle by particle, and orbit by orbit, the crown begins to look less like an original feature and more like the aftermath of something dramatic that happened in silence long before human eyes ever turned a telescope toward it. The first possibility is that the rings came from a broken moon, and this idea is powerful because it explains several things at once. The rings are overwhelmingly icy. They are located where Saturn's tides can keep loose debris from easily gathering into a large moon, and they may be young enough that some late disruption event is needed to account for their brightness. Imagine a moon made of rock and ice drifting too close to Saturn, not necessarily falling straight in, but moving through an orbit that brings it into the region where the planet's gravity pulls more strongly on the near side than on the far side, stretching the moon until its own self-gravity can no longer hold the outer layers together. This boundary is related to the Roche limit, not as a magical line where everything instantly explodes, but as a physical region where tidal stress can overcome the cohesion or self-gravity of a body, depending on its density, strength, spin, internal structure, and orbital path. So a differentiated moon with a rocky core and icy mantle might lose its bright outer ice, while some denser material either falls into Saturn, escapes, or becomes dynamically removed. In that version, the rings are not just ice, they are the remains of a lost world. The pale mantle of a moon spread into a disk, a body that did not survive as a sphere, but survived as orbiting light. This is why the broken moon hypothesis feels so haunting, because it turns Saturn's beauty into a kind of fossil. Not the fossil of life, but the fossil of an orbital catastrophe, with the fragments flattened by collisions, sorted by gravity, sculpted by moons, and slowly drained by ring rain. Another version of the same broad family imagines not simple tidal stripping, but a collision, perhaps between two icy moons, or between an icy moon and an incoming body such as a comet, where the impact launches debris into orbit around Saturn, and only a fraction of that debris lands in the right region to become a long-lived ring system. This collision scenario has its own quiet logic, because impacts were common in the early solar system and still occur, and a large enough strike could break a moon apart while preserving mostly icy debris in Saturn orbit, especially if the rocky portions are less efficiently captured into the ring region or later removed. Recent high-resolution simulations have explored whether the debris from colliding icy moons could naturally produce material that resembles the present rings and perhaps also contribute to the formation or evolution of some of Saturn's smaller moons. But the challenge is severe because the debris must have the right mass, the right composition, the right angular momentum, and the right orbital distribution, and it must survive long enough to spread into the system we observe today without becoming either a new moon too quickly or falling into the planet too efficiently. In this sense, the origin problem is not merely asking what broke, but asking how the broken material avoided every simpler fate. Because most debris in a planetary system either escapes, crashes, or reaccretes, while Saturn's rings occupy a delicate middle state, a disk of fragments that remain unfinished. A third possibility reaches farther back toward the birth of Saturn itself, suggesting that the rings could be leftover material from the ancient circumplanetary disk out of which Saturn's moons formed. Matter that never successfully became a moon because it stayed too close to the planet or was continually stirred and recycled. This older origin view once felt natural because giant planets form with disks, and disks form moons. And Saturn's rings look like the kind of remnant a planet might carry from its youth. But the difficulty is the same brightness that makes the rings so beautiful, because ancient exposed ice should have accumulated dark micrometeoroid pollution over billions of years, unless the rings are much more massive than they appear, or unless recycling, resurfacing, erosion, and selective loss continually refresh the particles. This is where the debate becomes especially rich, because young rings and ancient material are not always exact opposites, since the particles we see could be young in their present exposed configuration, while some of their source material could be older. Just as a beach may be newly shaped by a storm, even though the minerals in its sand are ancient, the rings may have an origin age, an exposure age, a dynamical age, and a surface age, and those clocks do not have to agree. Cassini made this complexity unavoidable by measuring the ring mass, the incoming dust environment, the composition, and the rate at which material moves between rings and planet, showing that any origin theory must satisfy not only a dramatic story of formation, but also a precise accounting of pollution, loss, brightness, and orbital evolution. If the rings were born from a shattered moon only a few 100 million years ago, their clean, icy appearance becomes easier to understand, But then, one must explain what destabilized that moon so late in solar system history. If they are primordial, one must explain why they are not much darker and why they have not been lost to spreading in rain. If they are the product of recycling, one must explain how repeated cycles of moon formation, breakup, accretion, and erosion can preserve a system that looks both ancient in complexity and young in brightness. The proposed lost moon, sometimes called chrysalis, belongs to one of the more elegant modern attempts to connect several mysteries at once, because it imagines a moon whose gravitational relationship with Saturn's larger satellites may have helped maintain the planet's tilt before the moon became unstable, approached too close, and was destroyed or stripped, leaving icy debris to become rings while much of the rest disappeared into Saturn or escaped the system. This idea is not a final verdict, but it is a beautiful example of how planetary science now treats ring origin not as an isolated event, but as part of Saturn's full dynamical history, including Titan's migration, resonances, planetary obliquity, and the gravitational architecture of the moons. The comet disruption possibility is also worth holding carefully, because a comet or small icy body passing too close could be torn apart by Saturn's tides, especially if captured or slowed into bound orbit. But the problem is probability and mass, since the present rings contain enough material that the source must be substantial, and the delivered debris must be mostly ice while avoiding too much dark contamination. A comet could supply ice, but producing the ring's mass and orbital order in the right place is not automatic. So such scenarios often need additional conditions, such as collision with an existing moon, capture during a rare dynamical encounter, or subsequent processing inside the Roche zone. This is the quiet discipline beneath the wonder, because every origin story must pass through conservation of energy, conservation of angular momentum, tidal physics, impact dynamics, collisional damping, and the chemical evidence left in the ice. Nothing can simply be placed around Saturn by imagination, because the particles must arrive with orbits that can flatten, collide, spread, and remain bright under the steady darkening of space. Even after the material forms a disk, it does not instantly become the rings we know, because collisions damp vertical motion, gravitational resonances carve gaps, embedded moonlets open lanes. Viscous spreading moves material inward and outward, and micrometeoroid impacts coat, eject, and redistribute tiny fragments. So the modern ring system is not the immediate photograph of its birth, but the long-edited version of whatever event began it. Perhaps that is why the origin remains unresolved in such an interesting way, because Saturn's rings are too orderly to be dismissed as simple wreckage, too young-looking to be comfortably primordial, too massive to be explained by a trivial accident, and too dynamic to preserve their first shape unchanged. They are evidence of a system where creation and destruction are not opposites, but stages of the same process, where a moon can die and become beauty, where a collision can become architecture, where leftover debris can become a luminous clock, and where every explanation must leave room for what the next spacecraft may reveal. In the stillness of a late-night sky, Saturn looks finished, but the origin of its rings suggests the opposite, that the solar system is not a museum of completed objects, but a place where worlds are still being rearranged, where moons migrate break, collide, and feed rings, where ice remembers violence by becoming light, and where the most peaceful-looking structure around any planet may have begun as something anything but peaceful. A lost moon, a shattered visitor, or ancient material that never quite became a world, still circling tonight in a thin white disk, unfinished, fading, and beautiful because its beginning remains partly hidden. Saturn's moons are not merely companions moving politely around the planet, small, pale worlds describing the darkness beside the rings. Because in the Saturn system, a moon is also a sculptor, a clock, a shepherd, a disturber, and sometimes a slow agent of destruction. And the reason these moons can both protect and damage the rings begins with a deceptively simple fact. Every ring particle is orbiting Saturn, but every nearby moon is orbiting Saturn too. And whenever their orbital rhythms line up in repeating patterns, gravity does not need to be strong in a single moment to become powerful over time. It only needs to arrive again and again at the right phase, like a soft hand touching a swing at the exact moment when the motion can grow. And this is why the rings, which seem so smooth from Earth, are full of sharp edges, braided strands, waves, gaps, scalloped borders, clumps, wakes, and moving distortions that look almost artistic until you realize they are mathematics made visible in ice. The smallest moons near the rings act like careful gardeners in some places, clearing paths and holding edges together, while in other places, their repeated gravitational pulls stir the particles, increase collisions, open wounds in the disk, and make the rings more vulnerable to spreading, grinding, and eventual loss. Pan is one of the clearest examples. A tiny moon embedded in the Encke gap of the A-ring, only about 28 kilometers across, small compared with Saturn, but large enough to dominate the local neighborhood of particles, and as it orbits inside its gap, its gravity scatters nearby ring material away from its path, helping maintain the opening, while also raising wave patterns along the gap edges, so Pan both preserves order and creates disturbance. Both keeps a lane clean and shakes the icy shorelines beside it. Daphnis does something similar in the Keeler Gap, but with an even more delicate drama, because this small moon has a slightly inclined orbit, and as it passes through the narrow division, it pulls ring particles not only inward and outward, but also above and below the ring plane, producing vertical waves that cast shadows when sunlight strikes the rings at a low angle. And in those shadows, Cassini saw one of the most astonishing truths about Saturn's rings. A disk that appears almost perfectly flat can be lifted into ridges and ripples by the gravity of a moon so small that it would be easy to overlook beside the planet's immensity. These gap moons are protective because they prevent local material from simply filling every space, maintaining the crisp architecture that makes the rings look organized. But they are destructive because clearing a gap is not a peaceful act. It is a constant redistribution of energy and angular momentum, a repeated scattering of particles into new orbits, a tiny gravitational negotiation that never ends. The same double nature appears on a grander scale with Mimas, a much larger moon whose orbital resonance helps shape the outer edge of Saturn's B ring and is closely tied to the region known as the Cassini Division. And here, the mechanism is not direct sweeping through a gap, but resonance, that subtle form of gravitational timing in which ring particles orbit Saturn in a ratio connected to the Moon's motion, receiving repeated tugs at nearly the same orbital phase. A single tug from Mimas would be almost nothing against the vastness of the ring system, but a repeated tug, accumulating over thousands and millions of orbits, can destabilize particles, pump up orbital eccentricities, and carve or maintain dramatic structure. So the Cassini division is not best imagined as an empty cut made once in the past, but as a living, dynamical zone where resonance continually influences where particles can remain dense and where they become depleted. This is one of the deepest reasons the moons both protect and destroy the rings, because a resonance can create an edge, and an edge is protection against uncontrolled spreading. But the same resonance removes material from certain orbital paths, increases particle motion, and helps convert a smooth disk into a structured, evolving system. In a quieter way, the moons act like boundary conditions in a mathematical problem, and without them, the rings would not look as crisp, but with them, the rings are never allowed to be perfectly calm. Prometheus and Pandora, the famous moons near the F ring, make the paradox more vivid because they have long been called shepherd moons, and the name suggests gentle guardians holding a narrow flock of particles in place. Yet Cassini showed that their behavior is more restless and complicated than the old shepherd image implies, especially for Prometheus, which repeatedly approaches the inner edge of the F ring, pulls streamers of material outward, creates dark channels or gores, and leaves behind patterns that evolve as the moon and ring particles continue around Saturn at different speeds. Pandora, outside the F ring, participates in the broader confinement and perturbation environment. But the F ring is not a quiet fence held neatly between two moons. It is a braided, clumpy, changing strand where nearby moonlets, resonances, collisions, and Prometheus's repeated gravitational encounters can create structures that appear, fade, stretch, and return. If the main rings are a wide, frozen river, the F ring is a thin, restless thread at the edge of the system, and its shepherds do not merely guard it, they disturb it into being visible as a complex thing. This pattern repeats across Saturn's ring system, because the moons do not protect by freezing the rings in place. They protect by actively shaping them, and active shaping always carries a cost. When a moon opens a gap, it prevents particles from occupying certain zones, but the particles removed from those zones do not vanish from physics. They gain or lose angular momentum, collide elsewhere, join waves, or contribute to gradual redistribution. When a moon excites a density wave, it transfers energy and angular momentum into the ring, creating a spiral pattern in which particles crowd together and spread apart, like slow breathing in a disk of ice. And the wave can propagate until collisions damp it, converting organized gravitational forcing into heat and microscopic disorder. When a moon creates a bending wave, it tilts the local ring plane and carries vertical motion outward, showing that even a disk flattened by collisions can be temporarily lifted by the right periodic force. These wave processes are not decorative ripples, but transport mechanisms, because they influence viscosity, spreading, local density, and the long-term evolution of the rings. The ring particles respond collectively, like a fluid in some respects, but individually like grains. And that hybrid nature makes the moon's influence especially rich. Since a moon can create a wave in the collective disk, while each particle still follows its own slightly perturbed orbit. This is why Cassini images can look like abstract art and a physics lecture at the same time, with tight grooves, spiral bands, and sharp margins that reveal the hidden presence of moons, even when the moons themselves are too small or too far away to dominate the image. Some moons even carry ring material on their surfaces, because Cassini found that small inner moons such as Pan, Daphnis, Atlas, Pandora, and Epimetheus show signs of being coated by ring particles, meaning the exchange is not one way, from moons to rings, but also from rings to moons. A gentle accumulation that gives some of these bodies their strange, smooth, equatorial shapes, as if the rings have been dusting them for ages, while they continue to disturb the rings in return. Enceladus adds another layer because it does not mainly sculpt the dense main rings in the same way as Pan or Mimas, but feeds Saturn's enormous diffuse E-ring through icy plumes erupting from its south polar region, supplying fresh material to a ghostly ring that stretches far beyond the bright main system. And this reminds us that moons can also protect a ring's existence by replenishing it, acting not as shepherds at the edge, but as sources, breathing new ice into the system. Yet even replenishment is not permanence, because particles in diffuse rings are strongly affected by radiation pressure, plasma drag, electromagnetic forces, and collisions with moons. So the supply must continue if the structure is to remain visible. The deeper pattern is that Saturn's ring system is not one object, but a coupled ecosystem of planet, rings, moons, magnetosphere, sunlight, and dust. And every moon near the rings changes the local balance between confinement and loss. The phrase protect and destroy therefore does not describe a contradiction in the moons, but the natural duality of gravity itself. Because gravity gathers and separates, confines and excites, builds edges and opens gaps, turns disorder into structure, and structure into motion. Without the moons, the rings might spread more smoothly, lose their sharp divisions, and become less visually complex. But with the moons, the rings are continually stressed, stirred, carved, and mixed, which keeps them beautiful while also making them dynamically alive. This is why the rings can feel so timeless from a backyard telescope and so temporary in Cassini's close view, because what looks like a static crown is actually being negotiated every moment by small worlds whose gravity arrives in pulses, ratios, and near misses. The moons are the reason the rings have lanes, borders, braids, and waves. But also the rings cannot be imagined as a peaceful frozen disk waiting unchanged through eternity. They are more like a quiet shoreline shaped by tides, where the same moon that draws the water into graceful curves also erodes the coast, grain by grain. And around Saturn, that shoreline is made of ice. The tide is gravity. The coast is a disk of orbiting fragments, and the erosion takes place not in foam or thunder, but in resonances, collisions, gaps, angular momentum exchange, and the soft blue-white silence of particles obeying the same laws that make worlds move. When Saturn's rings truly disappear, the solar system will not erupt. Saturn will not lose its orbit. Its moons will not suddenly scatter into darkness, and nothing on Earth will feel the change. Because the disappearance of the rings is not a catastrophe in the human sense, but a long planetary fading, a slow removal of ice, dust, and angular momentum from one of the most delicate structures we know. The first thing that would happen is not a dramatic breaking apart, but a gradual thinning of the main rings, especially in the regions where material is most vulnerable to inward transport. Micrometeoroid bombardment, electromagnetic charging, and ring rain. So the wide, shining disk that now makes Saturn instantly recognizable would become dimmer, less massive, less sharply defined, and more uneven, with some lanes losing brightness before others, some gaps widening, some edges becoming less clean, and some faint material either drifting inward toward the planet or outward toward zones where moons and resonances can capture, scatter, or recycle it. From far away, a future observer might first notice that the rings no longer blaze with the same white brilliance. Because as ice particles are lost and dark pollutants accumulate from interplanetary dust, the surface would likely reflect less sunlight, making the rings appear more ghostly and subdued, not gone all at once, but aging into transparency, like frost slowly evaporating from a window before dawn. The densest parts, such as the B ring, might persist longer than more tenuous regions because more mass can absorb more erosion and contamination, while thinner rings, such as the C ring or inner dusty structures, may fade more quickly under the combined effects of drag, plasma, ballistic transport, and rain into Saturn. But this sequence depends on details still being modeled. Because a ring system is not a single reservoir with one drain, but a layered disk where each particle size, each radial zone, and each electromagnetic condition changes the rate of loss. The second thing that would happen is that Saturn's upper atmosphere would continue receiving ring-derived material, not as visible snowfall, but as a chemical and dusty influx, with water products, tiny grains, and complex molecules entering high atmospheric layers, where some may vaporize, some may remain as nanodust, and some may alter local ionospheric chemistry in ways that future instruments could measure. This falling material would not pile up on a solid ground, because Saturn has no solid surface in the familiar rocky sense, only deeper and deeper levels of hydrogen, helium, clouds, pressure, heat, and fluid interior. So the rings would not end as ruins at the bottom of a crater, but as chemistry inside a giant planet, diluted into the atmosphere that once lay beneath their shadow. The third change would be visual and profound. Saturn would become more like Jupiter, Uranus, and Neptune, still a magnificent gas giant, still banded, stormy, oblate, magnetic, and encircled by moons, but no longer carrying the bright, broad halo that made it the emblem of planetary beauty. It might retain faint rings because the other giant planets do have ring systems, and Saturn may continue to possess thin dust rings supplied by small moons or impacts, especially if Enceladus keeps feeding the broad E-ring with icy plume material. But the grand main rings, the enormous A, B, and C ring architecture that dominates every iconic image, would be reduced or absent, leaving behind a planet that is scientifically rich but visually quieter, a world whose old crown has become a whisper. This would not make Saturn less real or less important, but it would change the way future civilizations understand it, because they might know the lost rings only through ancient images, preserved data, simulations, and the chemical fingerprints left in Saturn's atmosphere, just as we reconstruct vanished oceans on Mars, or infer shattered bodies from asteroid families. For them, the phrase Saturn's rings might sound historical rather than immediate, like describing a feature that belonged to an earlier season of the solar system. The fourth consequence would be dynamical, because the rings are not passive decoration, but part of an active gravitational environment. And as their mass declines, their ability to generate density waves, interact with embedded moonlets, coat small inner moons, maintain sharp disk structures, and participate in angular momentum exchange, would weaken. Tiny moons like Pan, Daphnis, Atlas, and other ring-adjacent bodies may evolve differently as the material around them thins, because some of their present shapes and surfaces appear linked to ring material accretion, and without a dense ring environment, their equatorial ridges, dust coatings, or local interactions could become relics rather than ongoing processes. Some moonlets embedded within the rings may be lost, exposed, merged, disrupted, or left behind as small icy bodies marking where denser material once flowed, while resonant structures driven by larger moons such as Mimas would no longer carve the same dramatic patterns if the disk being carved had mostly vanished. In this way, the disappearance of the rings would also erase a natural laboratory for understanding how disks behave around massive bodies, and that may be the greatest scientific loss, because Saturn's rings are the closest, sharpest, most detailed example we have of a collisional disk shaped by gravity, waves, resonances, self-gravity, impacts, and electromagnetic effects, a nearby miniature cousin of the disks that build moons around planets and planets around young stars. When the rings vanish, nature will remove from our neighborhood a living diagram of processes that operate across the cosmos. And although telescopes may still see disks around other stars, no distant protoplanetary disk can be crossed by a spacecraft with the intimacy Cassini had at Saturn. The fifth consequence would be historical rather than mechanical, because the disappearance would force us to reinterpret Saturn's biography, not as a planet that always wore rings and simply lost them late, but as a world whose appearance may have changed dramatically over its lifetime, perhaps ringless for billions of years, then suddenly bright after the disruption of an icy moon or a collision, then ringed for a brief interval, then ringless again. This means Saturn's famous appearance may be an episode, not an identity, and that idea is almost more unsettling than the loss itself, because it reveals how easily human imagination mistakes the present form of a planet for its permanent nature. If an observer had lived before the rings formed, Saturn might have looked like a golden giant without a crown. If an observer lives after they vanish, Saturn may again appear that way. We occupy the middle chapter, the interval when the debris is still luminous, still broad, still clean enough to dazzle, but already being removed by the normal machinery of physics. There is also a subtle atmospheric legacy to consider, because ring material entering Saturn is not just disappearing into nothing. It may influence ion chemistry, haze production, upper atmosphere composition, and energy balance, though the size and duration of these effects depend on whether the current influx measured by Cassini was steady over long time or partly transient. And this uncertainty matters because science does not yet know whether the rates observed near the end of Cassini's mission represent a long-term average, a seasonal state, or a temporarily enhanced episode. If the influx is episodic, the rings may decline in pulses rather than a smooth curve, with periods of stronger inward flow and calmer intervals. While if the loss is persistent, the end may be more steadily predictable. Either way, the trend points toward impermanence, not because Saturn is weak, but because rings are unfinished material, and unfinished material is always vulnerable to being finished by something else. A moon, a collision, a magnetic field, an atmosphere, a slow rain. In the last stages, the remaining visible rings might resemble the faint systems around Uranus or Neptune, narrow, dark, difficult to see, dependent on careful observation rather than immediate wonder, and then, perhaps, only dusty arcs, tenuous bands, or moon-fed traces would remain, while Saturn's main silhouette would become a clean, oblate sphere with moons crossing in front of it and shadows moving across its clouds, without the familiar bright disk receiving them. Future astronomers might still detect evidence of the vanished rings in the composition of the inner moons, the distribution of small debris, the history of Saturn's ionosphere, and the orbital structure left behind. But the spectacle would be gone, and what had once been obvious would become inference. That is what makes the question deeper than simple loss. Because when Saturn's rings truly vanish, the universe will not be poorer in matter, but it will be poorer in one arrangement of matter, one brief geometry of ice and light that allowed us to see orbital mechanics made beautiful. The atoms will remain somewhere, folded into Saturn's atmosphere, locked onto moon surfaces, scattered into faint dust, or redistributed through the system. But the pattern will be gone, and a pattern is often what beauty is. Tonight, when we look at Saturn, we are seeing that pattern before it dissolves, not in fear, but in awareness, understanding that the rings are not a permanent object attached to the planet, but a temporary sentence written around it. a sentence made of ice particles moving faster than bullets and fading slower than civilizations. And when the final letters thin into darkness, Saturn will still turn, still storm, still glow softly under the far sun. But the view that made us first fall silent will have become memory, leaving behind a calmer planet and a deeper lesson. Even at the scale of worlds, some of the most magnificent things are not built to last forever, only long enough to be seen. The most extraordinary part of Saturn's rings may not be their brightness, their size, or even the fact that they are disappearing, but the quiet possibility that we are living during the narrow interval when they can be seen at all. Because the solar system is not arranged for human wonder, it does not pause its long mechanical unfolding so that a small civilization on a blue planet can look up at the perfect time. And yet, somehow, in the brief window between the rings' possible formation and their eventual fading, our species developed eyes, mathematics, telescopes, spacecraft, spectroscopy, radio tracking, and enough patience to ask what those rings really are. Saturn itself is about 4.5 billion years old, born in the same ancient cloud that formed the Sun and the planets. But the rings may be far younger than the planet they surround, and if their present bright form truly formed tens or hundreds of millions of years ago rather than at the beginning of the solar system, then they are not Saturn's permanent identity, but a late chapter, a luminous event that arrived after the planet had already lived most of its life. This is the strange timing at the heart of the question, because a few 100 million years sounds immeasurably long to a human mind, longer than civilizations, longer than mammals in their familiar forms, longer than mountains can endure without being worn down and lifted again. But compared with the age of Saturn, it is brief, a late glow, a single soft measure near the end of an enormous planetary song. If an intelligent observer had existed around another star and looked toward Saturn with impossible clarity 1 billion years ago, there is a reasonable chance, depending on which origin model is correct, that Saturn might not have looked like the Saturn we know. And if another observer appears a few 100 million years from now, after ring rain, micrometeoroid bombardment, ballistic transport, viscous spreading, and electromagnetic loss have done their patient work, that observer may see a golden gas giant with only faint, dusty traces where we now see a wide, white crown. This does not mean the rings are vanishing quickly in the way a candle flame goes out, but it means their lifetime may be short enough on planetary scales that seeing them becomes a matter of cosmic luck, not inevitability. The timing becomes even more delicate when we remember that human observation itself is almost absurdly recent, because for nearly all of human history, Saturn was only a wandering point of light, one of the slow planets moving against the background stars, and only after the invention of the telescope did its true strangeness begin to emerge. Galileo saw it imperfectly in 1610, not as a clean, ringed world, but as a puzzling shape with strange side companions that seemed to change. Then Huygens recognized the ring nature in the 17th century. Cassini found structure within the rings. Later observers mapped divisions and shadows, Voyager revealed spokes and fine features, and the Cassini spacecraft finally entered the system deeply enough to weigh, sample, and listen to the environment that is slowly unmaking the rings. In the scale of Saturn's history, this entire human sequence, from first telescopic confusion to spacecraft measurement, is almost nothing. A tiny spark. And still, that spark happened while the rings were bright enough, broad enough, clean enough, and close enough to the present form for us to study them in detail. This is not proof that the universe is arranged for us, and science should be careful with such temptations, but it is a reminder that observation is always tied to timing, because what a civilization discovers depends not only on how intelligent it becomes, but on what the universe is doing during the short season when that intelligence is able to look. The rings are a perfect example because they are not a static object waiting forever to be understood, but an evolving system, and an evolving system can be missed. The equations do not care whether someone is watching as the particles collide, as dust darkens their surfaces, as resonances with moons carve gaps, as tiny charged grains follow magnetic field lines toward Saturn's atmosphere, as the disk thins through slow transport of mass and angular momentum. The process continues whether the observer exists or not. And yet here we are, inside the interval when a telescope in a backyard can still show a tiny oval with delicate handles, and a spacecraft from Earth could still dive between the planet and the inner rings before the great disk becomes something less obvious. There is a deeper scientific meaning in this timing, because the rings do not merely give us beauty, they give us a nearby laboratory for disk physics, and disks are one of the central structures of the universe. Stars form from disks. Planets form in disks. Moons form in disks. Black holes feed through disks. And debris disks around other stars preserve the leftovers of planetary systems. Saturn's rings are close enough that we can see waves, gaps, wakes, moonlets, collisions, particle sizes, optical depth, charging, and compositional gradients with a level of detail impossible in most cosmic disks. So our lucky timing is not only aesthetic, but intellectual. We are seeing a working model of processes that operate at scales from tiny grains to planetary systems. And we are seeing it before the model fades. That is why the disappearance of the rings feels worse than a simple change in appearance, because their loss would remove one of the clearest natural diagrams of orbital mechanics ever placed within reach of human instruments. Still, there is no need to turn this into fear, because the emotion Saturn asks from us is quieter than fear, closer to reverence, the kind that arrives when a thing becomes more beautiful after we learn it is temporary. A permanent ring would be magnificent, but a temporary ring is profound, because it means the solar system is still telling new stories long after its violent beginning, still rearranging moons, breaking bodies, scattering ice, making structures, and then returning them slowly to planets. Perhaps the rings began as a shattered moon, perhaps as debris from a collision, perhaps through a more ancient and recycled pathway that has not yet been fully understood. But in every scenario, they occupy a middle state between creation and disappearance. Not a finished world, not raw chaos, but a luminous compromise held together by motion. Our presence during this compromise is what makes the question almost dreamlike, because biological evolution on Earth, the rise of language, the making of glass lenses, the building of rockets, and the orbital decisions of Saturnian particles had to overlap in time for this moment to happen. Had the rings formed too late, we might have known only a ringless Saturn. Had they faded too early, we might have built myths around a quieter planet. Had Cassini arrived at another age of the system, it might have sampled a different ring mass, a different dust environment, a different chemical rain. Instead, our instruments arrived during the fading, but before the loss, during the brightness, but after enough evolution to leave evidence, during the mystery, but not after the mystery had closed. This is why the final answer to the title is not simply that Saturn's rings are disappearing, but that they are disappearing while we are here to understand what disappearance means. They are teaching us that cosmic beauty is not always ancient, that iconic forms can be temporary, that the present sky is not the default state of the universe, and that even a planet as familiar as Saturn is only familiar because we happen to meet it during one particular season of its life. When we look at the rings tonight, we are not just seeing ice around a planet. We are seeing time made visible. A bright arrangement of fragments that may have been absent for billions of years and may be absent again in the distant future. A structure large enough to humble us and fragile enough to remind us that scale does not guarantee permanence. Somewhere in the outer solar system, far beyond the warm blue air of Earth, those particles keep circling, inner ones moving faster, outer ones more slowly. The disk shaped by moons, darkened by dust, drained by rain, and illuminated by a sun that is already faint at Saturn's distance. And for now, the pattern still holds. For now, the crown is still there. For now, the light still reaches us. And perhaps that is the deepest reason we feel drawn to Saturn, because it is not only a planet with rings, but a quiet measure of how rare it is for a mind to open its eyes at the right moment in a universe where even the grandest things are passing through. Saturn's rings remind us that even the grandest beauty in space can be temporary. Thank you for drifting with Sleepy Space tonight. If this journey brought you peace, please like, subscribe, and rest well.